So now we'll have a talk by Maximilian from the LRZ, which is one of Germany's largest supercomputing centers, and therefore one of the world's largest supercomputing centers. Maximilian will talk to us today about sustainable AI infrastructure, something that I think has been discussed quite a lot around the world. How do you kind of maintain your AI infrastructures? How do you feed them? How do you water them? And how do you get them going? Max.
Thank you. We are set up. So, hello. Thank you for the nice introduction. And yes, we are talking about that's okay. About our efforts, plans, a bit of the history at the Leibniz Supercomputing Center, how we do energy efficiency, how we see our pathway to sustainable AI infrastructures. I brought some information on the systems we already have, some AI systems we had to have, and we optimized on another way. So I do spend a few words on who is the Leibniz Supercomputing Center. We are, as you mentioned already, one of 3 national supercomputing centers in Germany. Together with Stuttgart and Jülich, we share the share of the supercomputers with alternating architectures. So for Germany and Europe, we do ensure that we do not all have the same architectures, because we do want to have a supercomputing infrastructure that is heterogeneous, that has different architectures for our users that are mainly researchers. We in Munich are also responsible for 130,000 students of the 3 large Munich universities, but we also support IT services since over 60 years to research centers in Bavaria, Germany, but also in Europe. We are also part of EuroHPC. We do not have a EuroHPC cluster, but we do have a EuroHPC quantum computer. I will not talk a lot of that, but I will mention it later. We have to talk about power, and power comes from powerful machines. This is our flagship system, the SuperMOOC NG, established 2019. It's a Lenovo Intel system. I did bring some numbers. So this is 2019. There have been clusters with GPUs already on the market, but we have our own benchmarks. We know our users. And for us, a CPU-only system was the optimal choice back in 2019. So we have 311,000 cores with 27 petaflops of peak performance, and I brought you some numbers that we have a feeling, is that system used? And yes, it is. 9.6 billion core hours have been computed, 2.4 million jobs have been submitted to Slurm, over 500 projects have been supported, and 1,400 scientists are using that machine. But also the era of GPUs and AI is coming to LSC. That's why we have our extension of the SuperMOOC NG. NG is next generation, so SuperMOOC next generation phase 2. That is also a Lenovo Intel system that is built up in our facility since mid of the year. It's running in user-friendly mode, not in production mode. It has the Intel Sapphire Rapids and Intel Data Center Ponte Vecchio GPUs, and we expect production mode next year, beginning of next year. Throughout the conference, we heard a lot about HPC applications and why we do need those big machines. I do not want to mention too much, but I did bring one example about a flooding event in Bavaria that was quite extreme back in 2013. After that, the scientists of both universities joined their models for climate and hydrology. And we do not only have a computing facility, we also have a visualization center. So what you see on the left side is a cave, a 5-sided projection area when you actually can go inside and see. What you see here is the blue level is the water rising from the rainfall if there is no, if it continues to grow. What this enables our users and people, so we do have a lot of people coming to our center, we do tours and everything, in that you can feel and see exactly what we are computing on those large clusters. But we did hear a lot about the HPC applications in the conference. What I want to focus on is power consumption. And I brought quite old, a few years back, graphics from the top 500, where you have listed the average power consumption of the top 10 system of the top 500, the top 50, and the top 500. There was a time where the Green 500 was established. I do not want to talk too much about the Green 500, but it mainly focuses on the energy efficiency by comparing the energy spent and the petaflops enabling through the energy. This metric is highly discussed, and we think there might be optimizations to a metric that says how sustainable, how energy efficient is an actual system, than only comparing, for example, the benchmark numbers on petaflops with the power usage. This graphic was not continued, so I had to do this manually. And if we compare if we print the average energy consumption of the top 10 systems on the latest list in November, we are around 18 to 19 megawatts. Around, because one system didn't submit any energy consumption. So this trend is not linear. It's getting higher. So the energy consumption of all the systems is going up. Of course, if you have more money, you can buy larger systems. But of course, with the GPUs coming to the centers, there is of course more energy needed for running those. I do have a timeline of our HPC, mainly HPC and GPU systems, and the connected effort we took at LSE for energy efficiency. And we are very proud that back in 2012, with our supercomputer SuperMUC, it was the worldwide first hot water cooled system. You see here the board where you have the inlet and outlet lines for CPU and memory. This was a collaboration together with IBM, where back then, 12 years ago, nobody, not many people, cared about energy efficiency. And it was really hard to convince a vendor that we want to have a hot water cooled system. What is the benefit of a hot water cooled system? Well, we are going in our latest system with an inlet temperature of 42 to 43 degrees Celsius to cool the processors, the memory, and all the other parts. We are going out with 54, 55 degrees Celsius, so a plus of 10 degrees. We, after that, pump the hot water on our roof, where we have free cooling facilities, and in Munich, the temperature is not likely to be more than 2-3 days in the year over 40 degrees. So that means we do not have to add any chillers to 362 days of the year, where we have those free cooling, while we have a power efficiency usage, power usage efficiency value that is very good. I will tell you more about that later. Going forward in time, and I skip some of the systems because we do have heterogeneous systems for special purpose. We also did a research project with a German vendor, the CoolMUC3, that was the first 100% hot water cooled system without any fans. So this is quiet. It's really amazing how a quiet cluster looks like. The thing with SuperMUC was there are still fans for the networking, for the power connection. With CoolMUC3, we had the first system that was 100% hot water cooled. 6 years after SuperMUC, we got SuperMUC NG, and if you compare, maybe I go back, the image of the node from 2012 to 2018, you see 6 years of research and development is a huge add on metal. So this is still the CPU-only system where you have the processors and the memory and all the inlet and outlet temperatures going in. This is, of course, has a higher cooling capacity. And with that cooling capacity of SuperMUC NG, we did much better on the performance on the benchmarks as expected by the vendors and by us, because our infrastructure in-house, together with those boards, is so efficient back then that we have a PUE of 1.03. Sorry. What does this mean? So if we run the cluster, we need the power of the cluster, but we only have to add 3% of the power to power the infrastructure for cooling the system. This is very efficient, but I accept critics on that because we are calculating that manually. There is no certification, no standardization. If we power up another system, the PUE might influence positively or negatively, but we believe that this value is what it is for the system. Going further in time, we do have a collaboration project Terabyte with the German Aerospace Center. They moved 50 petabyte of their data to our institute, and they have every, I think, 8 or 16 hours a full circle of the Earth. So they actually need a good computational cluster. And I will later talk more about that, why this is important. We do have a huge cluster from NVIDIA A100 that is hot water cooled. Before, we had something else, but I keep you a bit waiting for that. I did talk about that, that's also direct hot water cooled with the GPUs. We don't have any pictures so far, but I think next year we will have some more information as this cluster will go in production. We are also planning our, so to say, pre-exascale system to be delivered in 2026. I cannot say anything about it because in these weeks that is to be contracted, and I hope as soon as it's concluded, we can talk about that. In parallel, on another branch, we do have quantum computing systems. It's not part of the talk, but I want to say this, that we do host as the superconducting quantum qubits a computer from IQM, where we have a lot of projects going on. How can we do hybrid HPC, QC computations? How this will affect energy efficiency, how we identify the applications, and part of the applications that we can use a quantum computer as an energy efficient accelerator as part of the project. We expect, together with the pre-exascale system, that we also have a 150 qubit quantum computer in place, closely connected to the HPC GPU cluster. We also have a trapped ion quantum computer delivered this year. So we built a lot of competence in the area of quantum computing. How this will affect energy efficiency, energy consumption among all the applications we have, we will see in the next years. So I already told you that energy efficiency at LSZ, we have been pioneering direct liquid hot water cooling that we are very proud of. We also reuse our heat for heating our offices, our buildings. But until 2 years, where the energy crisis in Europe happened, we actually have not been allowed to give our heat away, because if we're giving our heat away, we are an energy producing facility, we have to pay taxes, and this is complicated. But actually the situation changed, energy is needed, and we have a large campus with the Max Planck institutes, the universities, and now we have a prototype giving away our 5 to 6 megawatts of heat beginning of next year. But since we did have a lot of energy, we teamed up with a startup to do absorption chillers. That means we are producing cold air from hot water. On paper, this is not very efficient, but what can you do with the heat if you cannot do anything with the heat? So we did do this, but actually we are not using them anymore because we do not need that cold air, because all the commodity servers that are still fan cooled, we put in water cooled racks, so the efficiency of the whole system getting better. We are also doing energy aware scheduling. That means We reduce the clock frequency, for example, for some jobs if we know they are not CPU bound, they are, for example, data bound. We do have a broad instrumentation, and we do have a high frequency and high resolution monitoring system that is directly connected to all our systems. We have over 10,000 sensors in HPC AI and the QC systems. We can read internally, we can directly use the information in the scheduling and do the operational data analytics on that set of data. This is important to raise awareness internally. What is actually happening with our energy? Where can we improve our scheduling, the resource usage? Where can we improve the energy consumption to see also bottlenecks? We also can do different KPIs on systems or on center level. That means for the energy efficiency, you can calculate the PUE or other KPIs. They have all advantages or disadvantages, and that really depends what you want to know. Some colleagues of mine developed a model for the 4-pillar model that basically says if you want to have a data center that is energy efficient, it's not enough to focus only on hardware. It's not enough to have a good building infrastructure. You have to have a holistic optimization strategy. That means, for example, if you buy a hardware that is very energy efficient, a hot water cooling system, but your building infrastructure and cooling infrastructure is not able to cool the water down efficiently, I would say it makes no sense, but it depends, of course, what your needs are, because at the end, we need HPC resources, they need power, and they need to stand in some buildings. Important is also the HPC software stack, so the optimization of the resource, the tuning of the system, scheduling, and whatever you can do. But also, LSE has a large department for application support, so that means we teaming up directly with the researchers to optimize their application for our architectures. Because if the application is not optimized for using our hardware, it cannot be efficient. That's why we are keen on all those 4 pillars to really make a difference here. For the next slide, I would like to talk a bit of the NVIDIA systems as one of the vendors of the AI era. And if we look to the top 500 list I mentioned earlier before, of November, we see NVIDIA now has 27 entries in the top 500. Powerful systems, using a lot of energy, but of course, providing a lot of computational power. If you go out there and want to buy something, and we did that a few years back, you will find the GX A100, H100, Superport, whatever you can do. If you do not talk to somebody who can do this, those systems have been air-cooled. That means water cooling was only a supplement. That means your PUE is very bad. That means you need to spend 65 to 80% additionally to cool the system while running it. So 100% for running the system, additionally 65 to 80% of cooling it, because cooling with air is, from our perspective, not efficient. And if you stuck with that a bit, the energy consumption of the H100 is at maximum 700 watts per year. If you calculate it, 3.7 kilowatt hours at a normal utilization. If you compare that to average German household, it's a bit more, but it's more or less a German household per year. This is interesting. You can say it's bad, it's good, but what's really interesting is that NVIDIA estimated beginning of 2024 to sell 2 million of this H100. And if they are out there, just to get you a number of the energy consumption, this is 1.4 gigawatts without the cooling. If you have them fan-cooled, at 65% of it. We do have 5 of the DGXs A100 for our Munich Center for Machine Learning. They're here, they host each 8 GPUs. They are air-cooled, but in a water-cooled rack. So this rack is isolated, has here the heat, the heat switch, I forgot in English, from the water to the air, that you can cool the rack directly by water. But the PUE still is 60, is not good. Worse, this is the maximum amount we can put in such a rack, because the cooling capacity of this rack is 18 kilowatts, and each of them has 6 kilowatts, so there is a lot of empty space we cannot use for anything else, because all the cooling power is used by those 3 racks. We said, this is not good. We want to have another solution. And we know the numbers. We know the numbers. If we use water instead of air, the numbers are much, much better, a factor 3,400. And that's why we said, well, we are doing hot water cooling on SuperMOOC NG. You see it here in a large picture. Why cannot do we that on A100s? And the fact is, we found a vendor, we did a tender, and we found a vendor who actually did the A100s, Lenovo, the HGX-based nodes for A100s in one node. And here I said, you can put 24 GPUs in one rack. And this is the most efficient water cooling rack we have. Here, you can put 144 GPUs in one rack. We want to scale GPUs. We want to have clusters for our users that are powerful, that can make an impact for them, that can enable them to compute what they want. But this is not scalable. This is scalable. And the PUE drops from 165 to 103. And this is, of course, great for us. It's perfectly fitting in our infrastructure, and that is the way we see those GPU clusters should be designed, and we will see much more about that. So wrapping up a bit, the lessons learned towards the sustainability. What did we learn about the history with our HPC systems, the GPU systems we have in place? We believe a dynamic voltage frequency scaling, I did tell you about the clock frequency, is important. So that means you make a power-aware scheduling on the jobs, and usually we run our flagship system with only 68% of the nominal frequency, because we figured out this is not delaying the time to solution of the application, but it is actually reducing the energy cost a lot. We also have control of power capping and sleep modes. We run on 100% renewable energies, not because we have the power plants directly connected to the center, but it's contracted, so we believe it's true. The cooling infrastructure optimizations are also taking place in-house. We have a huge department working on that, having a lot of knowledge in this area. Last year, we removed the glycol from the free cooling. This is a substance you add to the water, that the water is not freezing, because I did tell you we might not have the 40 degrees in Munich, but we have freezing winters in Munich. So if we pump the water up off the roof, we have to be aware that it's not freezing, but the water has 50 degrees. It cannot freeze. It can only freeze if there is a problem. So we have some mechanical solutions for that, that we drop, that release all the water that is free of any chemicals if there is any failure, and so we can we do not have to use the glycol in our system. I told you about the waste heat usage. I also told you about the absorption cooling machines we had, not using anymore. And what will be upcoming with our phase 2 machine, what is on some clusters already implemented, that we include the job power usage in job protocol. So after job is finished, you get an email, it was successful, you have your log file, and also what power you used. This is not to penalize. This is not to prevent anybody using our system, but this is to raise awareness that actually, if you run a job on such a system, you're using power. So it's good that you use it because you have to. We have to compute our simulations and the applications. But be in mind, if you do it the most efficient way you can. And we do have a department for future computing technologies. We are looking in other accelerators like FPGAs or also quantum, how we can optimize the entire ecosystem we have in town. So closing with that slide, energy efficiency is essential for sustainability. I think we can agree on that. But we need a holistic approach and not only calculating gigaflops per watt. Aside from the carbon footprint, and this is also important for the funding agencies, there is also an important financial aspect. So if you have a more efficient system, you will save a lot of money on your power bill. And we need to foster awareness about the power consumption, also in-house. Not everybody in our center knows how much power we are using when we're running our applications, but also on the user side. And with that, I thank you very much, and I'm happy to get some questions.
Great, thank you, Max. So, are there any questions in the room?
Hi, Max. Thanks very much. That's a lovely presentation. Can you speak a little bit about optimizing the applications that you get from the user community, and just go a little bit about what you experienced there in matching the architecture, or what factors you have to consider?
So I try to, because the optimization of this application is a large process. What we usually do is, so for our flagship system, you cannot simply compute on it. You have to apply for it, and there's a review process. And while the review process is starting, we have a kind of a task force. So we send our people, my colleagues, going directly in the offices, do the development of the optimization directly together, because we have also access to maybe other libraries. They are also only available on the system. We do have development systems that have the exact same software stack as the supercomputer, but you can use really for development. And this is a process where we team up with the researchers to show them how to optimize it. Or also if you, so it's a large process from the development of the running, but also after that, if you have some data, we also help them with visualizing them. So I think we do have a lot of hardware, but we also do have a lot of competence, and we want to share that, and we want to enable all the researchers to actually use our systems as good as possible. The story is also that we have thousands of researchers in the area of Munich. Not all are aware that they can use our systems free of charge. That's all free of charge because we are publicly funded. That's why we have the review process. But we want to help them, enable them to get rid of those clusters in the basement of all the chairs and faculties where no energy efficiency is ever taking place, up to our center where we can do the best for energy efficiency, what we can do. Thanks.
Thanks, Max. Any other questions?
I just have a question. It seems like a no-brainer to go with hot water cooling than with fan cooling. So is there a cost drawback? So why aren't more people implementing this? And also, does the cooling then depend on the season of the year? And how does that influence the operation of the supercomputer?
So luckily, we are more or less season independent because we only need temperatures outside below 40 degrees. And if you have the historic numbers, this might change in the next years, but there are not so many days they are too hot that we do need extra chillers. But we do have extra chillers, and we do have, I don't have a picture of that, but actually we have a large building that are 5 floors. Of those 5 floors, we are using 1/3 of the space for our computing clusters. 2/3 we are using for the infrastructure to cool them. So also if our system is, we have to, how you say this, remove it from the system, nobody wants it. Why? Because you need the infrastructure we have in our basement in 2 floors to enable that water pumping that are large numbers we have there in the cycles. So it's a no-brainer to use it because it's more efficient, but you have to have in mind that you need a building that supports the infrastructure. And we were lucky that we built a new building when we moved out of Munich to a small town in the north in 2004, that those people thought about that you have to have infrastructure, a lot of infrastructure to run those systems. But yes, what we learned here, we learned in the development 2012, and we are optimizing that each cycle of the supercomputers, each cycle of a new system. Together, we partner up with the industry here that everybody can use that most efficient.
Okay, thank you.
Well, you're closer.
I think my question is closer to that. From my background of trying to cool computers down using water, it's always been that the cold water goes through the system to remove the heat. So I just want to understand the hot water that you're using. Are you pumping the hot water through, or are you getting the hot water out?
No, the inlet temperature is about 44, 45 degrees ingoing. And after that, we have an outlet temperature of 54. So actually, we're using hot water to cool the system. So we consider 45 degrees water as hot. So it's a warm, hot water cooling.
So how did you come up about the temperature that you need to go in? Can you drop it down than that 45?
So we want to have the inlet number as high as possible, because if it's lower, you have to cool it down. That's a development we have together with the vendors. We initially, on the first system, we didn't expect that we can go with that high temperatures, that the water flow is sufficient to cool the system. But we did see in practice it works. Also having Limpack running, it worked very well. So this is somebody my colleagues did and learned about the years, what is the highest temperature. So so some of my colleagues said, because I have no idea about that, for the next system that is really larger, maybe the temperatures need to be lower, because there is so much heat production in the system that this might not be sufficient. But we will see about that if we have it. And we will test it on our premise and optimize it as good as possible. Thank you.
Thank you. Very interesting talk. You may have partially answered this question, but what climate change modeling have you used to take into account the future of the system? In particular, if we compare to, say, South Africa, we continually experiencing increased heat here. So how would you adapt such a system to a scenario where your exterior ambient temperature keeps going up?
This is a very good question. So our planning years are 6 years for the next system and 12 for the second system. In this period, we do not expect any climate change that we cannot cope with our infrastructure we have in-house. But we were also visiting the tropical data center in Singapore. They have different challenges with humidity. The others here or in Australia have problems with the heat. It really depends on your premise how to do it. But the question is, how can we power those clusters and react on the premise? You mind, the solution that is worse is we buy some chillers, we produce more heat and support the climate change more. But I don't have a solution for that for other centers that might have 40 degrees on average, for example. I mean, the colleagues from Lumi, they are very happy because they're in the north of Europe in a very cold climate, and they say, why do you still continue building your computing centers in areas where there is only heat? The response is because we have to have computing centers. We need computing power somewhere. But if you can achieve the same power efficiency, I don't know. But we might come up with other other solutions for that, or also team up with the center here, maybe that our colleagues can have a dialogue on that.
Oh,
And then a follow-up question to that. Cape Town is right by the ocean. What about using large bodies of local water, whether it be ocean or lakes, for cooling, instead of relying on the ambient air temperature?
I'm actually not an expert on this. I only can say that we are not using so much water to cool because we are not losing so much. So we have, of course, closed cycles. But the question is how sustainable is it to use rivers like in Finland or the ocean for the globe if you cool your data center with that? Maybe there is more potential if you have facilities for your cooling where you can extract the heat to reuse it for other things, industry processes or whatever. So colleagues of us want to have a swimming pool close to the computing center, but nobody wants to build that. No, I'm joking, but I think using nature for cooling, what we are also doing with the roof, it's not optimal. It's not sustainable. We have to change that. But for the moment, that's the best we can do.
thank you. Any further questions? So I have one quick question. You mentioned the quantum computers, the quantum computers that you have. How much energy does a quantum computer use?
So we do use the IQM systems that are running on 7 to 8 millikelvin, and if they are cooled down once, they use for what we have now 50 qubits, 20 kilowatts constantly. But it's a tube. It's a large white tube, and you can put more qubits in it. So it's the same amount of energy for 100 or 200.
Really?
The difference is maybe you need more cables going out and in so that there's more interaction with the environment, that it might go up. But additionally to the quantum computer, you have a lot of measurement electronics. This is also a developing field in electrical engineering where you also have optimizations, but there we started with 40 kilowatts at the moment. So it really depends, but we are far away from megawatts. But a quantum computer is not, it's an additional device for HPC, so let's see where it goes.
Great. So with that, thank you very much, Max.
Thank you. Thank you for having me. It was a pleasure.
And Max is the final speaker, so thank you very much for attending and enjoy the rest of the conference.